Good morning, good afternoon, good evening, depending on where you are. My name is Gerald Verbeek. I'm the chair of the Conference on Foundation Decarbonization and Reuse and the moderator for these webinars that the conference organizers are putting together. Today we have a slight problem in that the announced presentations unfortunately cannot take place. But fortunately, we have found Marcel Bielefeld, that you already see on the side of your screen, willing to give a presentation. But because of time constraints from his side, we will have to shorten the webinar to about 45 minutes. And if there are still questions left, we will make sure that those questions will get answered through email. We apologize for this last-minute change, but I'm glad that at least we could continue this webinar series and make a very interesting presentation on foundation reuse. Before we get started, as you can see on the next slide, just a couple housekeeping notes. First of all participants will be muted during the webinar, but it doesn't mean that you cannot participate. Please use the Q&A button on your screen to submit your questions, and I will try to get those questions answered. As I said, if not in the webinar, we will make sure that all the participants will get an email with those questions later on. You already see the person who's going to make the presentation on the side of the screen, Marcel Bielefeld with Allnamics. And he was willing at the very last minute to give a presentation. And on the next slide you see is the title of that presentation, Load Testing for Foundation Reuse. And with that, Marcel, the floor is yours. You're still muted. So unmute yourself and start again, please.
That makes it much easier. Good morning, good afternoon, or good evening to all of you, depending on where you are. I'm glad I'm the possibility to share with you some thoughts about foundation reuse and decarbonization, and specific topic this afternoon, morning, evening, is the load testing for foundation reuse. And when I like to introduce and to start with the challenge we have as engineering in the industry to reduce the carbon footprint for all the things we do in the construction. As you are aware, or you can read about it, United Nations goals and the translation from that to the greenhouse gases protocol, split it in the scope 1, 2 and 3. I assume you're familiar with that. Scope 1 is the direct carbon footprint, for instance, of the power driving rig. Scope 2 is indirect, mainly electricity consumption on site. And 3 is all the carbon footprint in the value chain, so mainly materials and that what suppliers, the carbon footprint of the suppliers. And to illustrate the need to reduce raw materials, I've been a director of several concrete plants in the past, and we had several ships floating between our plant and somewhere in Germany getting aggregates for the concrete. And a ship like this is only one day of production in our plant. So we had several ships floating just continuously, let's say 6 days in a week, just bringing in raw materials. So there's a lot of materials going on in the construction, especially for the concrete, but a similar can be told about the steel from the furnaces. And to illustrate that, and research that ABT has been done, illustrating the impact of the foundation in the total construction industry. They have compared the impact of the environmental impact of our construction, and in 3 examples they noticed that the foundation and the basement are responsible for 30 to 60% of the environmental impact. That illustrates that our foundations, the foundations we produce, has a fair influence on the environment, not only in the carbon footprint, but also in the use of raw materials. So how can we reduce that material for foundations? Well, the solution is quite simple. We have to be smarter. I assume that you're all involved in designing and constructing foundations. If you do that more smarter, cleverer, then for sure we can reduce material. And one of the key is here the hidden safeties, which I'll explain to you later on, is hidden safeties in the current designs. And once there isn't foundation, just use it or use it extended for the superstructure that is coming on top of it. And how can we design smarter foundations? Now, an important topic in that is can contribute in that smarter designs is the use of pile load test results, because that reveals the true capacity of the piles as it is built, not as just designed. That is for newly constructed foundations the case, as built instead of designed, but especially also for existing foundations. Pile load testing reduces uncertainties in the total process of designing and constructing. All the assumptions we made during the design about the soil behavior, soil characterization, the values for shaft friction and toe resistance, they are all assumptions, sort of, and they all add additional safety, hidden safety to the pile design. And pile load testing can reveal that. And finally, the pile load testing will optimize the maximum allowable pile loads and makes a design more efficient in not only in money or in time what's needed to construct a foundation, but also in use of raw materials and the carbon footprint. Now, in a traditional approach, the way it's looked at existing foundations is that it is redesigned as a new foundation, rely on the foundation data which have been gathered from the archives, dimensions, cross-sectional area, the length of the pile, material, things like that. The drawings which maybe are available in the archives, and based on that foundation, of that information and about the foundation, the redesign is made. Soil investigation is sometimes newly performed, but quite often the old original CPTs or SPTs are reused. And in that way, if you redesign the existing foundation this way, then the outcome is like a completely new design, but also including all the factors of safety coming with this new structure, governing uncertainties in the design and the production. But the pile is already there, so the proof is not the design, but it's the test itself. So why not determine the pile capacity in the field instead of start it all over with all the assumptions in the design process? The pile is there, carrying the load for decades. So test the pile and eliminate the uncertainties. Uncertainties about actual pile dimensions of the foundation depth, the bearing layer, if that's unknown. That does not make that much sense if you know the capacity of the pile. And also the translation, the soil characterization and the interpretation of the soil investigations and make them to design parameters. The assumptions in that and the uncertainties in that are eliminated if you do a pile load test. And engineers in the geotechnique and foundations are master in dealing with uncertainties. If you compare that to engineers using other construction materials like steel or even concrete, they're much more secure about the performance of the material. We, geotechnical engineers or foundation engineers, have to deal with all types of soils, different types of soils, but even within a type of soil, all the parameters can be completely different. So there are a lot of uncertainties in the design and design methods we have to deal with. But there are also uncertainties in the production, because it's quite simple. In a prefabricated pile, concrete or steel or timber, you get what you see. You see the pile, it's driven in or fiber driven into the soil, and the dimensions of the pile, the length of the pile, that can easily be seen. But in cast in situ piles, no one sees what you get. Either in a board pile, a flying auger pile, or other type of piles, comes with uncertainties about cross-sectional area, the diameter and the pile length and other things like that. But also existing structures have uncertainties. At least there's uncertainty that the pile is there for decennia, decades, and it's proven in practice. It's not quite known how proven it is, because it's not proven until design load. It's only proven to the actual load. And that actual load is in general unknown. Design load is the load that never occurs. At least that's what we're hoping for. So if we split it in more detail, and I'm quite sure you're familiar with all those uncertainties, and you can even add your own uncertainties to that as well. But if you look at the design process of a new foundation, you have to deal with all the things and aspects of the soil characterization and the transfer of that soil data and the soil investigation results to pile factors. The use of software, some of them are only pushing the buttons, are not even aware of any engineering judgment what is needed to do proper foundation design. And then in the end, in all the design rules, there are safety factors, and quite often safety factors accumulating adds up to a certain design. And once the design is ready and the design drawings are ready, the contractor comes to site and install or fabricate the piles. And that's also come with uncertainties which quite often are not taken care of, but somewhere in the codes and somewhere in the safety factors, those uncertainties are certainly dealt with. It's all about experience, the skills of the piling crew, the sensitivity of a certain pile system for site conditions. Quite often mentioned, the morning pile is always different than just the ordinary Tuesday or Wednesday pile, and I doubt, well, I'm not sure about the Friday afternoon late pile. But also the existing structures still come with uncertainties, because if you want to do a redesign for an existing structure, you need proper data from that specific piles. You need the cross-sectional area, the diameter, dimensions. Often you can find them in archives, at least not often, but not always you can find them in the archives. But even then it's unsure and uncertain of the designed parameters which are in the archives are really as they are built. So the as built versus the as designed question. And then if there are older piles, the old methods for pile design, they're outdated. They are not up to date anymore. Nowadays, I assume our methods are much more detailed and much more better. Same is for soil investigation methods, either SPT, CPT, or laboratory tests. Old CPTs and old SPTs were all based on just ordinary data. Nowadays, it's all digital driven, digital files which can be read by the software. So even if you do a redesign for an existing foundation, that comes with uncertainties as well. So to deal with these uncertainties, we have to assess an existing foundation. But what we should not do is that we use the original design methods or codes. I think that's quite straightforward, because the modern techniques and the modern software is much more advanced than we had in the past time. So if we want to assess an existing foundation, at least use the modern methods to it. But also quite often overlooked is that we should not treat the foundation, existing foundation, if it were a new construction. Where in a new construction, it's dealt with uncertainties in the design process and even in the construction process. We do have that issue with existing foundations, because the pile has already proven itself in practice. With the risk that if we treat it as a new constructions, that the uncertainties and the factors of safety to deal with that are stacking up and making just the pile too safe. And at third, if we assess an existing foundation, we have to keep in mind that although we think that the pile has proven over time, over decades, it's there, the actual load history is still unknown. We do not know up to which level the pile has been effectively loaded and thus effectively tested over its lifetime. Dealing with uncertainties have always all to do with a safety philosophy. I'm sure you're familiar with this type of graphs. Forget about the numbers along the axis, but in general, the strength should be higher than the stress. But the stress and the strength comes with a variation. There's an average and there's variation on it. If you look at the load, or in red, the stress, load composition distribution because we are quite secure about the weight of construction, so we know the static load on the piles, but we are not so good in estimating wind, snow, rain, and other type of loads, giving a sort of scattering results and where the stresses can vary. That's in red, and the same can be said about the strength given the variability of the materials we use. For instance, concrete, there's an average and there's a variability along that average. And there's in this safety philosophy is there where the strength, the stress exceeds the strength, you get failure, and that's the small triangular down under probability of failure. There in that small area, the stress is slightly higher than the strength, and there's the risk of failure. And the idea about reducing uncertainties is about being more secure about the strength, the blue distribution of strength, make them smaller, less variability, so that this happens. And as a result, that the triangle there below is still the same, the probability of failure is still the same. But in the end, the average, which is needed to reach this safety, is reduced. So if we are able to reduce the uncertainties, then we can deal with lower strength averages without reduction of the safety, because that's important. We don't want to reduce the safety of the structures we construct. So how to reduce those uncertainties? And that's for new structures as well for existing structures the same. Just test the pile as it is built. Then you have no influence of if the pile is different constructed than according to the drawing as built versus designed, or maybe there are some slight imperfections in the pile. That doesn't count if you just just load the pile and test the pile. However, pile testing is often not done. Yes, it's a matter of money as always, but also we rely fully on the design methods we use and the parameters we use, and we rely on the workmanship of the piling contractor and especially the crew performing the pile. So I can see that as well, that we trust the design methods, that we trust the workmanship and the skills of the contractor. But yeah, control is better. Trust is good, but control is better. Or should we control to trust? And if we do a pile load test, then we give this trust. Because if we do it by redesign, control of existing foundations, we have to rely on uncertainties about the parameters of the foundation itself. Is it built as it designed? About the assumed or maybe checked on-site pile length, the soil investigation, either original or newly performed, and we redo the design as if it were a new design, including the factors of safety of a new structure. So if we want to skip that all, then we just do the test that overcomes all those uncertainties. And it's often not done because it is also not often so simple. The practice limits quite often the possibilities of pile load testing because the pile is difficult to access. It's always underneath a superstructure because there's the foundation for. But even it becomes more complicated with groundwater, with the soil, basements and things like that, which makes it hard to access the pile top to test. But hey, we are engineers, and engineers are educated and are in practice problem solvers by profession. It's our profession to solve problems. So instead of say, wait, we are not able to test these piles, don't focus on the obstacles, but just make sure it can happen. And raise the question for yourself, what is needed to make a test happen? And I'm pretty sure that with some energy of all the engineers like you and ourselves, almost any pile can be tested. Any pile under a superstructure can be tested. Exceptions are there, but a general rule, it should be possible. And to show that to you, I have two simple examples, relatively simple, in where existing foundations has been investigated, assessed, and I just want to bring those forward with you. and see what we can learn altogether from these two specific sites. There are sites in the Netherlands. Bennebroek is near Amsterdam. If you're familiar with the Netherlands, you know where Bennebroek is, but let's say roughly in the neighborhood of Amsterdam. And the other case is in Rotterdam. Rotterdam is one of the larger cities of the Netherlands. In Bennebroek, we are looking to the foundation of house blocks. Those are built in 1965, and under these blocks are timber piles, which was quite common in that time, with concrete followers. And because the age of these foundations of about 60 years raised the question: are these foundations still fit for purpose? Are the people living in these blocks, are they safe, and will they be safe in the near future? Now, these timber piles with concrete followers looks like this. A timber pile is driven into the bearing layers, and on top of it is slightly hollow or with a different connection. A concrete follower is driven on top of it. And the main reason for that is that by the follower, we make sure that the top of the timber pile remains below water level. That means that the top of the pile is continuously in wet conditions to avoid dry rot, and the water preserves the timber pile and makes sure that the durability of the pile is for many decades. So the timber pile with an oplanger, a concrete follower, is quite common in the Netherlands for buildings in 1960s. And this is how you see it is done nowadays. The concrete follower can be either circular or square, like the photo on top of it. And there is in general a steel cylinder in it, and the steel is driven into the timber pile to make it a good connection between the timber pile and the concrete follower. And in this way, the top of the timber pile is driven below the groundwater level. Back to our houses from 1965, we noticed that the pile lengths were unknown, but that the diameter of the pile tops were around 24 centimeters. Here we see a newly made CPT. And of course, quite often as assessment of existing foundations, a redesign is made. First, the load calculations were updated, the weight of the floors, the facades, the roof, and the variable loads like wind and rain are added to that, and that required a pile capacity of roughly 10 tons. And we did the pile testing to make sure that those loads can be met by the piles, to demonstrate that actual capacity, to make sure that there's a safe situation. But we exceeded the load test a little bit higher than that, just to see if there is hidden safety in the structure. Now the conditions were specific here because during the test people are still living in their homes. We had to minimize the nuisance, of course, and out of question was any damage to the buildings. Not even a minor crack was allowed. So what we did is dig a hole, excavate a pit to access the foundation, remove all the material what's in there, the mud, the water, added pumps to it and drainage to make sure that the water table was low enough to have a work situation, but also safe and stable enough to work in. We dig deep enough to expose the top of the pile by at least, let's say 2 feet, 600 millimeters. And we had some additional clearance at the front to bring in the monitoring equipment. We cut out a piece of the pile, we removed that part, prepared both surfaces and put in between the hydraulic jack to make it possible for loading the pile. So what we use is the superstructure as a counterweight to push the pile downwards. And next to the load, the hydraulic jack, we have of course to monitor that load. So additional were calibrated load cells and 2 monitor settlements extensometers and a reference frame to monitor the settlements of the pile during loading it. And once everything is set up, our engineer can sit out in the sun. Most often it's rain anyway, but can sit in the sun and do the test, not in the pit, but just outside. Start the measurements, and as you are aware, static load test takes a while. So performing static load test is in general a combination of waiting and drinking coffee. The results of the static load test of this site in Bennebroek are presented here. On the left side, the monitored forces from the calibrated load cells as a function of time. And on the right side, you see the settlement displacements of the top of the pile in the time. You see clearly the load steps that have been made and how the pile responds on that load steps. And you see for the last load step, there was some creep in the pile. But in the initial load steps, the piles of course has been in use for a while. It was all horizontal steps also in the displacement. And if you make a graph of horizontal the load and vertical the displacements, you see here the load settlement diagram of these piles, and then dotted in it, let's say the calculated more or less hyperbolic load settlement graph from this particular test. And you see that we had the load was limited to 200 kilonewton here. In fact, it was limited because the pile had continuously movement downwards under this load. Some people call it a geotechnical failure, but that's wrong. There is no failure of the soil. In contrast to concrete and steel, if you do a test and you have failure of the concrete, then you have broken concrete. In our profession, where we use soil as construction material, there's no failure, although it's often called that way. I think, in fact, we're here at the limits of what the soil can do, both on the shaft friction as on the toe. And how to derive from this load, the maximum test load of almost 200 kilonewton, 20 tons. Quite often the load capacity is taken at the displacement of the pile, which is roughly 10% of the diameter. In this case, with 24 millimeter, we should have found a capacity of 190 kilonewton. And to remember you, what we required for these particular houses was a capacity of just 102, let's say 10 tons was needed, and 19 tons, 19 tons, what is proven by this static load test. So for the people living in Bennebroek, there are no worries about their foundation because there's sufficient hidden safety in those piles. Even higher loads could have been possible. The 100 is what is required, and 190 can be delivered by the piles. Some questions remain because there's variation of the soil conditions across the site. So how much is that soil variation of the soil, and how much does it affect the bearing capacity between those piles? Because we did test the pile. Did we test a strong pile or just a soft or weak pile? So therefore, at least test a couple of piles. One is none. At least 3 piles to capture not only the average of those piles, but also the variability, and get us confidence in the test results. That's the case in Bennebroek. The other case is in Rotterdam, an old construction, a national monument nowadays. It has been constructed over 100 years ago. Original constructed as a 2-story factory, and that factory is has been famous because that produced all the motorized bicycles, the Poeg. And so this is a well-known factory from the past. However, the building was demolished during the Second World War and has been rebuilt and extended, even with an extra floor at that time. And if you look at the original graphs, here you see the original building left during construction on the right side, as it was at that time. But after the World War, the construction has been build new facades, it has a different look, although the structure itself has remained the same. And nowadays it looks like this. Met a modern, even a rooftop on top of it has been added to it, because the building has been redesigned, repurposed into apartments. So instead of an industrial building, it became apartments. So additional rooftop apartments were added. The existing basement has been used and extended for parking lots, and between the existing floor levels, additional floor levels has been added. Now, as you can imagine, that with all these adds, additional floors, there was additional loads on top of the pile. So the question is that this change from the use in an industrial building to apartments, what does it affect the foundation? Get higher loads, that's for sure, but is the foundation fits for a new purpose? So assessing that and the existing foundation and answering that question about fit for purpose, what shall we choose for? Is it a redesign, or shall we test, or shall we do both? Again, here, trust is good, but control is better. So we did both, redesigned the piles, but also did the test to control, to have trust in the solution. Was quite a little bit more complicated to assess the piles because it was below the basement. But again, we are engineers, you're engineers, we all are able to get solutions, to get things done. So here as well, we were able to come to the top of the pile, and we were able to do a similar static load test as we shown to you in Bennebroek. The redesign showed and required pile load, working load of 117 kilonewton, almost 13 tons, with a design value of 16 tons, and the test load was 180 kilonewton, because in that we added 2 times negative skin friction. Tests are done with limits, of course, limits of the jack, limits of the pile itself, and of course we have to make sure that the superstructure is not damaged during the test. And also here the results of those load tests. You see on the left side again the force as function of time, and on the right side the displacement, the settlements versus time. On the right side you see 3 graphs, slightly different, because we measure on 3 positions on top of the pile. The slight difference shows that the force was not perfectly axial aligned with the pile itself, giving a slight bending there as well. And on the left side we see the force, and with a small loading step during the 1, 2, 3, 4, 5th loading step. And then we compare, put it in an old diagram, the force on the horizontal axis and the settlements of the vertical axis. Again, here we had also a pile of 240 millimeters. So when we look at the displacements at 10 times the diameter, 24 millimeter, we find an ultimate of 270, but that's a little bit close to the limits of this pile. So we have calculated in this particular with an ultimate load of 225 kilonewton. Compare that to what we needed, minimum pile resistance of 180, then still whereas sufficient safety and higher loads can be applied on this particular pile. However, there's no information about the variability of the soil. So the question is then, if we test 1, 2, or 3 piles, what will be the maximum applied load on the other piles which are not tested, and which maximum load should be derived from the tested piles. If we wrap it all up and see what we have discussed about the topic of pile testing and making smarter foundations and reduce not only the carbon footprint but also reduce the amount of material we use for our foundations, then it comes to that modern construction industry requires smarter foundations. In our world, sustainable construction is important, and smart foundations can be part of that. That can lead to reduction of the carbon footprint and can lead to reduction in the use of raw materials. That's not only good for the environmental reduction of raw materials, but also the transport of it, the getting the raw materials from the soil, from Mother Earth. That's good. But also applying less materials is quite often also good for the budget. Pile testing can help making more efficient and more smarter foundations. That's valid for new installed piles, where when we do tests, we can use proven values for the capacity of the pile instead of assumed design parameters and assumed design values. And for existing piles, it's even more valuable to do pile load testing, because then it clarifies uncertainties and we can mobilize hidden safety. Pile testing under existing superstructure can be complicated, but quite often it's possible without damaging the existing structure. Yes, if you have to remove a part of the floor that is damage to the floor, that should be repaired, but it's not structural damage to the structure. And what we find in experience with all the pile tests we've done over years, that in general, quite often higher loads can be applied than what has been taken care of according to the redesign or new design pile capacities. Of course, not always the case, but in general, it seems to be that pile tests show higher loads. That has to do with the hidden safety in the original design and in the construction phase. If we apply higher loads on the existing pile, that does not say that the safety is reduced. It's just that every construction has to be safe, but building safer than safe, that's not quite necessary. So just as I explained, by the safety philosophy, reducing higher loads is not reducing the safety, it's just optimize the capacity of the pile and the loads which are in a newly built structure necessary. And once the existing foundation is not sufficient capable to carry all its load, then just add foundation elements where it's needed. That can either be just piles, adding piles there where it's needed, but sometimes it's just sufficient to distribute the loads over more piles by adding stiffer beams, pile caps, or even plates to distribute all the loads over more piles. So, and that's the end of my contribution for this afternoon, morning or evening, wherever you are, that the pile load tests make foundations more efficient and sustainable, not only for in reuse conditions, but also for new foundations. Well, this is my contribution for today. I'm looking forward to reactions from your side or questions, but first give the word to Gerald.
Thanks, Marcel, for your presentation. For those of you that logged on a little bit later, you may have wondered, why are we talking about this and not about pile testing in Canada or reuse foundations in Canada? For various reasons, we had to change the program at the last minute. Our colleagues from the Winnipeg area were unable to join us, and that's why I asked Marcel to step in at the last minute. And even though there's a time constraint, because he could only be here for the first 45 minutes instead of the full hour that we normally have for this webinar, I'm very grateful that he did that and was able to step in, and that's why you heard this presentation. If you have questions, as always, please use the Q&A box. But before we do this, before we go to some of the questions, Marcel, we're talking in this case about foundation reuse, but we're also, of course, in the conference dealing with decarbonization. Decarbonization, as you mentioned at the very beginning, smaller diameter pile, less material, that's the big gain. And when you think about load testing, quite often we only do a proof test to a certain amount, multiple of the design load, but we don't go to a load test to establish the ultimate load. Would it not be much more useful if during the initial construction we already do that, that we test to the ultimate load to get a better understanding of what is the safety or this hidden safety is in there, so that hopefully we can design, even for new foundations, more appropriately and don't have this large unknown hidden safety in our foundations. Or how do you see that?
Yeah, Gerald, I think that's a good point. That in fact we should pile load test to distinguish in two types of pile load tests. One is to prove that the design load can be reached. Thus, if you reach the design load, that particular pile is proven to be okay, fit for that purpose. The other type of test you're referring to, and that's if you test the pile up to, well, they call it failure. I like to avoid the word failure, just to check what's the maximum capacity is, to stretch the load up to the maximum what the pile can bear. And if you do that more often, you are more secure about the real factors of safety we're using. We're stacking factors of safety during the design process and in the construction process, and by testing up to the ultimate of the pile's capacity, you become more aware what that safety really is, and that can help us to making foundations more efficient. So reduce carbon print, reduce the material use. That should be done more often. Yes.
Okay. Couple of questions that we still have for about 4 more minutes before I will let you go to meet your schedule. First question came in during the pilot testing. The foundation pile was disconnected from the superstructure. Were any measures taken to compensate the loss of support to the superstructure above?
In this case, no, but yes, you have to be care of that. So what they are monitoring the settlements of the superstructure during this, and some temporary support is added to it. In this case, where we were quite sure about the pile's capacity and the neighboring pile, which was nearby, there are no precautions had taken. But normally we'll take care of that. Yes, good question. Yeah, for sure.
And based on your studies on those two sites, how much was the design life of the structure affected in a positive or a negative way?
Can you repeat that question, Gerald? We had some issues with the internet.
Based on your studies on these two sites, how much was the design life of the structure also played a role in assessing? Because it's obviously not only the load that the pile can handle, but it also has to do with the condition of the pile and the design life. Did that alter the views on the outcome of the load test results?
The short answer, no, it didn't alter that, but yes, that's for sure. If you look for reuse or extended life of piles, either on the existing structure or on a new structure, there are two issues. The fit for purpose is always referring to not only to the load and if the pile is capable to resist that load, but also to is it fit for purpose not only now, but also in the future. So if the condition of the pile, material of the pile is good for now, will it be good in the future? Not always necessary to have a prediction of the lifetime, but at least you should be aware that the condition that now is good enough for now, but also in the near future. The piles they're in Bennebroek 65 years old. If I refer to a lot of timber piles in Amsterdam, some of them are even 400 years old, and they are regularly tested and get a sort of not guarantee, but also indication if there is maintenance needed in the upcoming 25 years. So yes, you have to take care of that as well. That's for sure.
Okay. That's all the time we have for questions. Thank you so much, Marcel, for stepping in at the last minute, making it fit your schedule, even though we have to make it slightly short. Greatly appreciated. Just a couple of closing remarks. There's lots more information, of course, on our website at foundationreuse.com. We try to post all the webinars there, also all kinds of papers, reports there that we can find. And if you see something that is published, please let us know. We will post it there as well, because what we are trying to do is really make people think that foundation reuse is an option. and consider that as an option whenever they deal with a situation where you have a reuse of a potential reuse of a foundation when the superstructure is destroyed or replaced or no longer function. And there you see heading on the website, and then you can go to the resource center and get this information. We will have the other thing that we will do is we have these regular webinars, generally speaking, the first Tuesday of every other month. So the next one will be in early February, and then we'll have in early April of next year. And of course, in between that, and that will be seen on the next slide, we will have our next conference, the third annual conference on Foundation Decarbonization and Reuse, which will be held in March of 2026. We put on there 25, but it's really 2026. I just see that now. Apologize for that error, but I hope that you consider coming to Amsterdam to learn even more about this topic of foundation reuse. And with that, I want to thank again you as attendees for being here. I want to thank Marcel one more time for making this presentation, and I look forward to seeing you here in Amsterdam, or hopefully attending a virtual webinar again in the near future. Thank you very much.